When we look at the universe from far away, it often appears calm. A planet hangs quietly in darkness. A nebula glows without urgency. A galaxy turns so slowly that it seems almost motionless. From a human point of view, space can look silent, empty, and strangely peaceful. But this impression is misleading. The universe only looks calm because most of its most violent processes unfold on scales that do not match human senses. They are too large, too distant, too fast, too slow, or too energetic to feel immediate from where we are. What appears still is often under enormous pressure. What appears silent is often filled with radiation. What appears stable may only be balancing collapse against heat, motion, or gravity. This is one of the most important ideas in astrophysics. The cosmos is not quiet because nothing is happening. It is quiet because we are very small, and the deepest forces of nature do not announce themselves in human terms. On Earth, violence usually has familiar signals: sound, shock, heat, motion we can see directly. In space, those signals change. There is no atmosphere to carry sound in the ordinary way. Distances are so extreme that even explosive events can appear serene. A star can release more energy in a moment than human civilization could use in ages. And yet, from far enough away, it still looks like a steady point of light. That difference between appearance and reality matters. It means the universe often hides its intensity behind beauty. A glowing cloud may be a region where stars are being born under gravity and pressure. A brilliant point in the sky may be a dead star compressed into a state of matter almost impossible to imagine. A dark region may contain so much gravity that even light cannot leave it. And yet, to the eye, all of this can seem elegant, smooth, balanced, even restful. Part of that comes from scale. Human experience is built around middle-sized things: rooms, mountains, weather, bodies. The universe is built from scales far outside that range. Stars are large enough to crush matter under their own weight. Galaxies are large enough that their structure emerges from gravity acting over billions of years. Black holes warp space and time in ways that no everyday object ever could. Even emptiness is not truly empty, because radiation, fields, and high-energy particles move through it constantly. So when we say the universe looks calm, what we really mean is that it does not resemble the forms of motion we are used to noticing. A drifting galaxy does not look like a storm. A supernova remnant does not look like an explosion in the earthly sense. A black hole does not look like a collapsing building. The physics is real, but the visual language is unfamiliar. Another reason the cosmos appears gentle is time scale. Some of the most important events in the universe happen almost instantly by astronomical standards, but still remain slow compared to human expectation. Other processes take millions or billions of years. A star may spend most of its life in apparent stability while an immense struggle continues inside it, with gravity pulling inward and pressure pushing outward. That balance is not peace. It is tension held for a very long time. And in astrophysics, long tension often matters more than sudden drama. The shape of a planet, the life of a star, the structure of a galaxy, and the motion of matter around a black hole all depend on forces that are always acting, whether or not they produce a spectacle in any given moment. This is why the universe can be both beautiful and merciless at once. Its beauty comes partly from order, and that order is often created by extreme conditions. Gravity gathers matter. Pressure resists collapse. Radiation carries energy outward. Rotation shapes disks, rings, and spirals. Magnetic fields channel plasma into arcs and jets. Temperature determines what matter can become. Behind every quiet image of space, there is usually a negotiation between forces. That is what makes the dark so interesting. Darkness in the universe is not passive background. It is where structure forms, where energy moves, where matter falls together, where time stretches, and where the laws of physics become easiest to see in their purest form. The night sky can feel peaceful, and in one sense it is. But it is peaceful in the way a great ocean can look peaceful from a cliff. Its surface may seem calm. Its depth is another story. To understand the universe, we have to accept that its stillness is often an illusion of distance. The calm is real as an experience. But beneath that experience is a cosmos ruled by force, pressure, motion, and scale, far beyond anything the human body evolved to understand directly. And that is where this journey begins. Not with the comforting appearance of the stars, but with the hidden physics that gives them their shape. If there is one force that shapes the universe more quietly and more completely than any other, it is gravity. It does not flash like radiation. It does not roar like an explosion. It does not announce itself in bright color. And yet gravity is the reason stars exist. It is the reason planets form. It is the reason galaxies hold together. It is the reason matter does not remain scattered forever through the dark. Gravity is the quiet architect of the cosmos. On Earth, gravity feels ordinary because it is always present. We stop noticing it for the same reason we stop noticing air. It is constant, reliable, invisible. But in the wider universe, gravity is not just the force that makes objects fall. It is the force that gathers structure from emptiness. Left alone, matter in space would remain thinly distributed. Gas and dust would drift. Small irregularities would stay small. Gravity changes that. Wherever a region of space contains slightly more matter than the region around it, gravity becomes just a little stronger there. That stronger pull attracts more matter, and as more matter arrives, the pull grows stronger still. This is one of the most important patterns in astrophysics. Gravity builds by accumulation. A cloud becomes denser. A dense region becomes a core. A core grows hot. A star is born. The same logic works on larger scales. Dust grains in young systems collide and stick. Small bodies become larger bodies. Larger bodies become planetesimals. Planetesimals become planets. Nothing in that chain happens quickly by human standards. But over time, gravity turns unevenness into structure. It is patient but relentless. That patience matters. Gravity does not need to act suddenly in order to be powerful. Much of cosmic history is simply gravity having enough time. Given enough time, it pulls gas into stars. It arranges matter into galaxies. It guides moons around planets and planets around stars. It shapes the paths of objects even when they never touch. In that sense, gravity is not only a force, it is a kind of long-term order. Even the shapes we associate with beauty in astronomy often come from gravity working together with motion. A spiral galaxy keeps its form because gravity binds billions of stars into one rotating system. A ring system remains coherent because gravity organizes countless particles into orbital structure. A protoplanetary disk flattens because matter falling inward also carries angular momentum. Again and again, the same lesson returns. The universe is not arranged. It is gathered. Gravity is also unusual because it never switches off. There are forces in nature that can cancel, shield, or balance in complicated ways. Gravity is simpler in one respect. For ordinary matter, it always attracts. That gives it enormous reach. A magnet can dominate nearby metal. Radiation can dominate hot plasma. But gravity dominates scale. It is weak when compared with some other forces at the level of particles, yet it becomes decisive when enough mass is involved. And the universe contains a great deal of mass. This is why gravity governs the largest things we know. You do not need gravity to explain a spark. You do need gravity to explain a star. You do not need gravity to explain a chemical bond. You do need gravity to explain a galaxy. It is the force that becomes more important as the stage becomes larger. There is also something almost paradoxical about it. Gravity creates both stability and collapse. It holds planets in orbit, but it also drives stars toward compression. It gives galaxies their structure, but it can also pull matter into black holes. It allows worlds to exist, yet it is always trying to make matter fall inward. That tension is everywhere in astrophysics. A star survives because pressure pushes outward while gravity pulls inward. An orbit remains graceful because forward motion resists falling directly toward the center. A galaxy endures because countless individual motions exist inside one shared gravitational field. Without gravity, the universe would be thinner, colder, and less structured. But gravity alone does not create beauty. It creates the conditions in which beauty can emerge. It gives matter reason to meet, reason to remain bound instead of disappearing into formless distance. That is why gravity deserves to be called an architect, but because it repeatedly turns scattered material into lasting form. And it does so almost silently. Only attraction, acting across distance, year after year, age after age, until clouds become stars and stars become systems. But much of what we call calm is really gravity at work, shaping the dark so slowly and so completely that the finished result appears natural. And once gravity has gathered enough matter together, another force begins to matter just as much. Because the moment matter starts to fall inward, the universe begins to ask a new question. What pushes back? Gravity may be the force that gathers matter, but it is not the whole story of a star. If gravity acted alone, every star would simply collapse inward. Gas would keep falling toward the center, density would rise without limit, and the structure would never stabilize. The reason a star can exist for millions or billions of years is that something pushes back. That opposing force is pressure. A star is, in a very real sense, a long negotiation between gravity and the outward pressure created by extreme heat in its core. Gravity pulls matter inward, compressing the gas more and more tightly. As the gas is compressed, its temperature rises. And when the central region becomes hot and dense enough, nuclear fusion begins. Fusion changes everything. Hydrogen nuclei begin to combine into helium, and in the process, a small amount of mass is converted into energy. That energy moves outward through the star, first as radiation and then, in many layers, through convection and heat transport. The result is pressure directed away from the center. It is this outward pressure that prevents the star from immediately collapsing under its own weight. So when we look at a star and see a calm point of light, what we are really seeing is a balance being maintained. That balance is called hydrostatic equilibrium, and it is one of the most important ideas in stellar physics. A star survives because inward gravity and outward pressure remain closely matched. If gravity becomes too strong, the star compresses further. If pressure becomes too strong, outer layers expand. Over time, the star adjusts itself around this tension. That is why stars are stable without ever being truly at rest. Their stability is dynamic. It depends on continuous fusion, continuous heat flow, continuous pressure, and continuous gravity. The interior of a star is not peaceful in the ordinary sense. It is dense, hot, and violent beyond anything the human body can meaningfully imagine. Yet from far away, this sustained violence becomes visible as steady light. There is something profound in that contrast. The star shines because it is resisting collapse. Its light is not a decorative feature added to the universe. It is evidence that gravity has gathered enough matter to ignite fusion, and that pressure is now holding the structure open against further compression. In that sense, every star is a physical argument between falling inward and pushing outward. And that argument cannot last forever. A star lives only as long as it can keep generating enough pressure to resist its own weight. Once the fuel in its core begins to change, the balance begins to change with it. New stages of fusion may follow, or they may not, depending on the star's mass. But the central truth remains the same. A star is not a flame floating in space. It is a temporary equilibrium built from gravity, heat, and pressure, and held together for a while in the dark. No star lasts forever. A star can remain stable for an immense length of time, sometimes for billions of years, because pressure in its interior continues to resist gravity. But that balance depends on fuel, and fuel is finite. The long life of a star is not endless peace. It is a temporary arrangement, maintained only as long as the core can keep producing enough outward pressure to hold collapse back. That is why the death of a star is not really a sudden event. It is the slow failure of equilibrium. At first, the change happens deep inside the core, where hydrogen has been fused for most of the star's life. As that hydrogen is used up, the center can no longer generate pressure in quite the same way. Gravity begins to win again, and the core starts to contract. But this contraction does not simply destroy the star. It also heats the interior further, and that extra heat can ignite new stages of fusion in surrounding layers. So the structure becomes more complicated. The core shrinks, outer layers expand. The star grows larger, often becoming a red giant, or, for much more massive stars, a supergiant. To an outside observer, this can look almost graceful. The star swells, brightens, and changes color. But underneath that beauty, the physics has become unstable. The old balance is gone, and a new one is harder to maintain. This is one of the most remarkable features of stellar evolution. A star often becomes most dramatic when it is running out of time. For smaller stars, the ending is comparatively gentle. The outer layers drift away, forming expanding shells of glowing gas. The hot, exposed core remains behind, compact and dense, no longer powered by full-scale fusion. For larger stars, the ending can be far more violent. Fusion continues through heavier and heavier elements until the core reaches a point where pressure can no longer support the weight above it. Then collapse happens quickly, and the star may end in a supernova. What matters is that the death of a star is not separate from the life of the universe around it. When stars die, they do not simply disappear. They transform matter. They throw heavy elements back into space. Carbon, oxygen, silicon, iron, and many of the ingredients needed for planets and life are linked to stellar evolution and stellar death. In that sense, the ending of a star is also a form of distribution. Material once trapped inside one bright object is returned to the wider cosmos. That is part of why dying stars matter so much. They are not only the end of something stable, they are the beginning of new structure elsewhere. Clouds enriched by older stars can later form new stars, new planets, and new systems. The universe remains dynamic because nothing stays in one form forever. Even something as constant-looking as a star is only a long-lived phase in a much larger cycle of compression, fusion, collapse, and return. So when stars begin to die, the universe does not become quieter. It becomes stranger. And from that strangeness comes some of the most extreme objects we know. When a star like our Sun reaches the end of its active life, it does not usually explode in the most violent sense. Its outer layers drift away, and what remains is the core, small by stellar standards, but still holding a large fraction of the original mass. That remnant is called a white dwarf. A white dwarf is one of the strangest objects in astrophysics because it is held up by a form of pressure that has almost nothing to do with ordinary heat. In a normal gas, pressure comes mainly from particles moving faster as temperature rises. In a white dwarf, the matter has been compressed so intensely that another kind of resistance takes over. This is electron degeneracy pressure. The name sounds technical, but the idea is profound. Electrons are quantum particles, and they obey rules that prevent them from being packed together arbitrarily. When gravity squeezes matter far enough, the resistance no longer comes mainly from thermal motion. It comes from the structure of quantum physics itself. Matter pushes back, not because it is hot in the ordinary way, but because there is a limit to how tightly electrons can be forced into the same state. That means a white dwarf is not a star in the usual sense. It no longer shines because fusion is actively supporting it. Instead, it is the leftover core of a star, glowing with stored heat while gravity is held in check by quantum pressure. It is dense beyond ordinary intuition. A large amount of mass is packed into a volume comparable to a planet. The result is an object whose gravity is intense, whose surface is extremely compact, and whose matter exists in a state that does not resemble familiar solids, liquids, or gases. What makes white dwarfs so important is that they reveal a boundary. Earlier in a star's life, gravity is balanced by pressure produced through fusion. In a white dwarf, fusion is no longer the main support. The star has crossed into a different regime where quantum mechanics becomes the thing preventing further collapse. This is one of the clearest examples of how the universe moves from everyday physics into extreme physics without ever breaking its own laws. There is also a limit to this arrangement. If a white dwarf becomes too massive, electron degeneracy pressure is no longer enough to hold it up. Gravity can force matter into an even more compressed state, leading toward the next level of stellar remnant. This critical threshold, known as the Chandrasekhar limit, is one of the most important mass boundaries in astrophysics. It marks the point where one kind of matter support fails and something more extreme must follow. So a white dwarf is both an ending and a threshold. It is the quiet remnant of a once luminous star, and at the same time, a demonstration that matter itself has hidden forms of resistance that only appear under immense compression. It is what remains when a star has lost its ordinary light, but not yet surrendered completely to gravity. And in that compact, fading remnant, the universe reveals that the weight of matter is not measured only by mass. It is also measured by the strange quantum rules that decide how far collapse is allowed to go. If a white dwarf shows how far matter can be compressed while the electrons still hold the line, a neutron star shows what happens when even that is no longer enough. A neutron star forms when a massive star dies, and its core collapses so violently that electrons and protons are forced together. Under that pressure, they combine and produce neutrons. What remains is an object of extraordinary density, one in which a large stellar mass has been crushed into a sphere only a small fraction of the original star's size. It is difficult to overstate how strange this is. A neutron star is not simply a smaller star. It is matter driven into a state that barely resembles anything familiar. The atoms that once structured ordinary material are no longer intact in the usual sense. The object becomes a compact body whose interior is governed by nuclear physics, quantum pressure, and gravity operating at almost unimaginable intensity. And yet it remains, in its own way, stable. That stability comes from neutron degeneracy pressure and from the strong nuclear interaction, which together resist further collapse. Gravity is still trying to force the remnant inward, but matter has entered such an extreme regime that new forms of resistance appear. This is one of the recurring themes of astrophysics. Every time gravity drives matter deeper into compression, the universe reveals another layer of physical law. Neutron stars are also remarkable because of how fast they can rotate. When the original stellar core collapses, it shrinks dramatically, and angular momentum is conserved. The result can be an object spinning at extraordinary rates. Some neutron stars rotate many times each second, and when their magnetic axes are misaligned with their rotation, they can sweep beams of radiation across space like cosmic lighthouses. These are pulsars. To an outside observer, pulsars can appear almost mechanical, so regular that they seem artificial. but their precision is a natural consequence of collapse, magnetism, and rotation combined inside one of the most extreme remnants in the universe. Their magnetic fields can be astonishingly strong as well. In some cases, neutron stars become magnetars, objects whose magnetic intensity is so great that it can affect surrounding plasma, radiation, and the structure of matter itself. These are not merely dense stars. They are compact laboratories of extreme physics where gravity, nuclear matter, relativity, and electromagnetism all become impossible to separate cleanly. What makes neutron stars so important is that they sit near a threshold. A white dwarf is already far beyond everyday intuition, but a neutron star moves deeper still, to the edge where matter is compressed almost as far as it can be without vanishing behind an event horizon. It is one of the last stable forms matter can take before gravity threatens to win completely. So a neutron star is not just the remnant of a dead star. It is a physical limit made visible. It shows how the universe behaves when collapse is pushed almost to completion, and it reminds us that even in the aftermath of stellar death, structure does not immediately disappear. Sometimes it becomes denser, stranger, and more revealing. And at the edge of that compression, another possibility begins to wait: the black hole. Few objects in the universe have attracted more attention or more misunderstanding than black holes. They are often described as cosmic monsters that swallow everything around them, but that image is too simple. A black hole is not a hole in the ordinary sense, and it is not some magical tear in reality. It is what can happen when gravity compresses matter so far that no known pressure can stop the collapse. At that point, something more profound occurs. Gravity no longer behaves like a strong pull acting inside space. It begins to reshape space and time themselves. This is the key idea. A black hole is not just an object with intense gravity. It is a region where space-time has become so strongly curved that escape beyond a certain boundary is no longer possible. That boundary is called the event horizon. The event horizon is not a solid surface. You would not crash into it the way you would crash into a planet. Instead, it marks the limit beyond which all possible paths lead inward. Once anything crosses that boundary, even light can no longer return to the outside universe. That is why black holes appear black. They do not shine on their own in the usual way, because the horizon prevents emitted light from escaping back out. What makes black holes especially strange is how they affect time. According to general relativity, stronger gravity means slower time. Near a black hole, this effect becomes extreme. To someone far away, clocks near the event horizon would appear to run more and more slowly. Signals sent outward would be stretched, reddened, and delayed. In that sense, a black hole does not only bend paths through space, it distorts duration itself. This is one reason black holes feel so difficult to imagine clearly. Human intuition is built in a world where space seems flat, time seems uniform, and gravity seems like a downward force. Near a black hole, those assumptions fail. Distance, motion, and time no longer behave in familiar ways because the geometry underneath them has changed. And yet black holes are not just theoretical curiosities. We infer their presence through the behavior of nearby matter. Gas falling toward a black hole can heat to extraordinary temperatures, forming an accretion disk that glows intensely before the matter crosses the horizon. In some cases, magnetic fields and rotation help launch enormous jets of energy far into space. So while the black hole itself remains dark, the region around it can become one of the brightest and most energetic environments in the universe. What is important is that the black hole does not create these effects by acting like a cosmic vacuum cleaner. Matter can orbit a black hole just as planets orbit stars if it stays far enough away. The black hole becomes dangerous not because it mysteriously pulls harder than anything else at every distance, but because near enough to it, the the structure of space-time becomes overwhelmingly steep. That is why black holes matter so much in physics. They are places where gravity reaches its most uncompromising form, and where our ordinary picture of reality must be replaced by something deeper. They show that the universe is not built on fixed stage scenery, with matter moving around inside it. The stage itself can curve, stretch, and close. In that sense, a black hole is not only an extreme object, it is a reminder that space and time have shape, and that under enough gravity, even time can begin to fall inward. To human intuition, empty space sounds safe. If there is no air, no weather, no ocean, no forest, and no surface to collapse beneath your feet, then emptiness can seem almost peaceful. But the vacuum between worlds is not gentle. It is only quiet in a way that hides its danger. The first reason is radiation. On Earth, we live beneath an atmosphere and inside a magnetic field that absorb or deflect much of the high-energy radiation constantly moving through space. Outside that protection, the universe is far more exposed. Charged particles from the sun, cosmic rays from distant astrophysical events, and other forms of energetic radiation pass through the dark whether we notice them or not. That matters because radiation does not need sound or flame to be destructive. It can damage living tissue, disrupt electronics, alter materials, and accumulate harm slowly over time. A habitat in space must be designed not only to provide air and pressure, but also to reduce exposure to something the eye cannot see directly. In that sense, one of the great threats of deep space is invisible. Then there is the vacuum itself. Vacuum is often described simply as the absence of matter, but in practical terms, it changes almost everything. Without air, heat does not move through convection. A warm object cannot cool by passing heat into surrounding gas, because there is no surrounding gas. Energy has to leave mainly through radiation. This makes thermal control a serious engineering challenge. In sunlight, surfaces can heat intensely. In shadow, they can become extremely cold. The transition between the two can stress materials over and over again. Vacuum also means exposure. No atmosphere burns up micrometeoroids before they arrive. No protective weather layer softens incoming particles. Tiny grains moving at high speed can strike with surprising energy, and over long periods, even small impacts become part of the environment a structure must endure. This is why empty space is not really empty in the human sense. It contains fields, particles, radiation, plasma, and energy moving across enormous distances. It may look still, but it remains active. The danger is simply less theatrical than danger on Earth. There is no roar, no crashing wave, no visible storm front approaching. Instead, there is a continuous background of exposure, and yet this violence is not random. It is connected to the same physics that shapes stars, stellar remnants, and galaxies. Radiation comes from energy released in extreme conditions. High-speed particles come from magnetic fields, explosions, and energetic astrophysical processes. Even the harshness of sunlight in vacuum reminds us that stars are not decorative lights. They are engines of power. So when we think of empty space, it is worth abandoning the idea that emptiness means passivity. In the universe, emptiness can burn. It can erode, it can irradiate, it can slowly break down both matter and life. The vacuum is silent, but it is not benign. It is one more reminder that the dark is ruled not by stillness alone, but by physics acting continuously in forms that only appear calm from a distance. By this point, a pattern has become difficult to ignore. The universe does not produce its most important structures under gentle conditions. It produces them at the edge of instability, where gravity, pressure, heat, radiation, and motion are all competing at once. What we often describe as beauty in astronomy is very often the visible result of extreme physics held in temporary balance. Stars exist because gravity compresses matter until fusion begins. White dwarfs exist because matter is packed so tightly that quantum pressure becomes the thing preventing further collapse. Neutron stars exist because compression pushes matter beyond the ordinary structure of atoms. Black holes appear when even those last forms of resistance are no longer enough. Again and again, the same lesson returns. The universe runs on extremes. That does not mean every region of space is violent at every moment. Much of the cosmos really is thin, cold, and dark. But the structures that matter most, the ones that illuminate, organize, transform, and redistribute matter, are usually born where conditions become severe. Energy is released when matter falls inward, when stars ignite, when stellar cores collapse, when magnetic fields accelerate particles, and when radiation escapes from environments under extraordinary stress. Even large-scale beauty often depends on this. A nebula may look soft and luminous, but its shape can reflect shock waves, stellar winds, ionizing radiation, and old explosions. A galaxy may appear calm, but it is held together by gravity acting across incomprehensible distances, while stars are continuously being born and dying within it. A brilliant accretion disk around a black hole exists because matter is being heated to immense temperatures as it spirals downward. The peaceful appearance remains real. But it is often the peace of distance, not the peace of inactivity. This matters because it changes how we think about the universe. It is easy to imagine the cosmos as a passive backdrop, with a few dramatic exceptions scattered through it. A more accurate picture is that the universe is always being shaped by competing forces, and what looks stable is often only stable because those forces are balancing one another for a while. In that sense, equilibrium is one of the great themes of astrophysics. A star is an equilibrium. An orbit is an equilibrium. Even the long life of a galaxy is a kind of dynamic equilibrium. But these balances are never simple. They persist only because physical laws allow tension to be sustained across immense spans of time. When that balance changes, structure changes with it. Stars swell, collapse, explode, or cool. Matter shifts state. Radiation escapes. Gravity reorganizes what remains. So the dark is not merely where things disappear, it is where the universe does its deepest work. Inside that darkness, matter is compressed, heated, accelerated, ionized, and transformed. Time passes differently in strong gravity. Light changes as it climbs out of deep wells of curvature. Even emptiness becomes active when filled with radiation and fields. The calm surface of the cosmos is real, but beneath it lies a continuous physical drama. That is why extreme physics is not a rare side story. It is the engine of cosmic structure itself. The universe does not merely contain extremes. It depends on them. By the end of this journey, the universe begins to look different. It still contains the same stars, the same darkness, the same distant galaxies and silent horizons. But once you understand even a little of the physics behind those images, the calm appearance of the cosmos no longer feels simple. It becomes layered. The beauty remains, but now it carries weight. What seems still may be held together by pressure resisting collapse. What seems empty may be full of radiation, magnetic fields, and energetic particles. What seems permanent may only be a long-lived balance between forces that are always trying to push matter into some new form. That is what physics means in a dark universe. It is not just a set of equations written to describe remote objects. It is the structure beneath appearance. It is the reason stars shine, the reason planets hold their shape, the reason matter gathers instead of remaining forever diffuse, and the reason some of the most beautiful things in the cosmos are also the products of immense stress. In human life, darkness is often associated with absence. We imagine it as the place where things vanish, where visibility ends, and where certainty becomes difficult. But in astrophysics, darkness is rarely empty in that simple way. It is often the medium in which the most important forces become visible through their consequences. Gravity is invisible, and yet it builds stars and bends time. Pressure is invisible, and yet it keeps stellar interiors from collapsing too soon. Radiation cannot always be seen directly, and yet it transports energy across space and shapes the environments around stars and remnants. Even vacuum, which seems like the absence of everything, turns out to be an active condition that changes how heat moves, how matter survives, and how vulnerable life really is. This is one reason the universe feels so profound when viewed scientifically. The deeper the explanation becomes, the less the cosmos seems reduced by understanding. In many ways, it becomes more mysterious because the visible surface of things is only the beginning. A star is not just a light. A black hole is not just a dark circle. A galaxy is not just a pattern in the sky. Each is the visible trace of deeper rules acting over immense scales of space and time. And those rules are not arbitrary. They are consistent. They are patient. They are severe. They do not care whether we find them intuitive. That, perhaps, is the strangest comfort of physics. The universe is not gentle, but it is intelligible. It does not arrange itself around human expectation, yet it can still be understood. Even the most extreme objects we have considered, white dwarfs, neutron stars, black holes, radiation fields, collapsing cores, remain part of one continuous physical story. Nothing is outside the laws, only outside ordinary intuition. So when we look into deep space and feel that mixture of calm and unease, wonder and distance, we are responding to something real. The universe is beautiful, but not because it is mild. It is beautiful because structure can emerge from force, because order can exist inside extremes, and because even in the darkest regions, the laws of nature remain at work, shaping reality with astonishing precision. That may be the final lesson of the dark. It is not empty. It is not passive. It is not silent in any absolute sense. It is where physics becomes visible through everything it makes possible.